Hello and welcome to the video lectures for this week. Today we are going to start a first very important application of information theory with a set of very fundamental results on lossless data compression, or more simply just data compression. When you say data compression, to distinguish between lossless compression and lossy source coding. For example, when you compress an image or compress a video using some standard like JPEG 2000 or MPEG-4, you introduce some loss in the sense of distortion. While when you compress, for example, a file, for example, you zip a text file, well, when you unzip it, the file is exactly what you had before. There is no loss. This is called lossless. And nevertheless, without paying any price in terms of distortion, we can actually compress sources. So, for example, data files, text files, all sort of sources, as long as their entropy, as we will see, is finite and in fact is well defined. So we will deal mainly with something called discrete sources. Discrete sources are basically sequences of random variables that take on values in a discrete alphabet. For example, a binary source, the alphabet is 0, 1. A ternary source is going to be 0, 1, 2. And, if you have a source like text represented as ASCII characters, well, this would be, for example, a byte, so 256 characters, all possible octet of 8 bits. Okay, so in particular, for the moment, we treat a particularly simple model of discrete sources, which is called discrete memoryless sources. So here is the definition. A discrete memoryless source, or more briefly a DMS, is a discrete time random process, so it's a sequence of index random variables, x1, x2, x3, defined over a discrete alphabet x, such that those random variables are mutually independent, which means the joint PMF of any vector extracted from the sequence breaks down into the product of the marginal distributions of the individual random variables, and it turns out that these are independent and identically distributed with a common marginal PMF P sub x. So P sub x here denotes the PMF according to which each xi is distributed. Okay, so imagine this is like, if you want, a sort of random number generator that you use to generate random sequences, and these random sequences are the realization of the source. For example, a random sequence of zeros and ones will be a realization, or a specific sequence of zeros and ones, it will be a realization of a binary discrete memoryless source. Okay, so now at this point we can define what we mean by a fixed to variable length lossless source code with block length n. This is definition 9 here. Well, this is a map, so it consists of an encoding function that maps sequences of length n of the source, so over the source alphabet, over binary sequences of variable length. So we denote D as the binary alphabet 0, 1, and D star denotes the set of all sequences of any length. So this could be of length 1, or length 2, or length 3. It depends. It depends on the length of the output sequence is also a function of the input source sequence. And the code is also defined by another map, G, that maps binary sequences into source sequences. And those two functions, encoder F and decoder G, have the property that for every sequence X in Xn, G of F of X is equal to X. In other words, if I concatenate the encoding function, so I go from from some specific sequence X, I apply the encoder, I obtain some binary sequence B. B may be of some length that depends on X, and then I apply the decoder function G, I obtain back X. So this condition that the decoder is able to undo perfectly the encoder is the lossless condition. So any source sequence X can be perfectly represented by this encoder, because the decoder is going to recover it perfectly. Okay? Good. So going on with definitions, why we should do this? I mean, if you have X, at the end you recover X, why we should do this? Well, because given a NFG, so this will be a lossless source code with encoding function F, decoding function G, and operating on source blocks of length N, we can consider the associated length function. The length function L of X is the length of the binary sequence F of X. Remember, F of X is a binary sequence because F is see from here, F is a mapping between source sequences and binary sequences, but those binary sequences may have different lengths. So in general, for every X, there is a binary sequence, which is F of X, with a certain length. The number of symbols, so the length of the sequence, we call it L of X. And then we can define the average output length, big L sub n, as the expectation of this length function. So this will be the expectation of L of random sequence Xn, which means sum over all X's in the possible sequences, their length times their probability. Okay, that's the usual definition of the expectation operator. And finally, we can define the data compression rate of the scheme to be the normalized average length per source symbol. So you see, if we apply the encoder to randomly generated source blocks of length n, we obtain this variable length L of X of n. We take the expectation, so this will be the average length. We divide this by the length of the source sequence. Well, this is rate is in bits per source symbol. Okay? So for example, you may have a text represented in ASCII characters, and because this text is compressible, we will see what it means later on. When we zip it, well, we get a much smaller file. Then what you can do is to count all the ASCII characters in your file. This will be n. Count the length of the output in bits, and then this will be the compression ratio. Now, if we do this to many files generated according to the statistics of the source, we can take the average of those, and this will be the rate defined in this way. So it makes sense to measure the goodness of a compression scheme in terms of this rate, so bit per source symbol, and of course we want to have schemes for a given source statistics px. We want to have schemes that achieve this rate as small as possible. So the question will be, what is the smallest possible rate? What is the fundamental limit for data compression? And are there schemes that can approach or achieve this limit? Okay? So before talking about this, let's define a few more things. So we define the kth extension of an NFG lossless code simply by concatenation. So suppose that I have a very long sequence X of length n times k. Then I can divide this sequence into blocks. So there will be a first block x1 of length n, a second block x2 of length n, until a kth block. Okay, so the sequence now is divided into blocks, and then I can apply the encoding function independently, block by block. So I map this using the function f. Okay, so the resulting concatenation of the binary sequences f x1 concatenated to f x2 concatenated to f x3 up to fxn forms the output of this kth extension code. Okay. And then we can generalize this idea and define the star extension code as the collection of all k extension codes for any k. So this will be, in general, the star extension code of a certain lossless code is going to be a mapping between x star to d star, because we can take sequences of arbitrary length, block them into blocks. Notice that typically we consider very long sequences, so even if the last block is not exactly n, well, there will be a little bit of approximation, say integer rounding there, but this will count very little in the rate, because when we divide by the length of the whole sequence, this little say rounding error will not count, will count in a vanishing way. So we can say that for a given n, the star extension code is essentially a mapping between sequences of arbitrary length of the source alphabet into binary sequences of whatever length. Okay. Now, why we do this? Well, because if we have an algorithm that works on block length n, okay, maybe it's a very good algorithm, but the block length is fixed, then we don't want to design a different algorithm for every file length, right? Because files data come with variable lengths, you cannot say beforehand, right? So normally you would design a scheme that works for a certain length n with good performances, and then you want to apply the scheme by extending it into many blocks to files of arbitrary length. Okay, so this is essentially for a reason of practicality. But this practicality reason poses a problem. The problem is that, let me explain this. So we are interested in decoding the kth extension code. And this means that we need to be able to parse the output sequence. So let me make here an example. So suppose that we take a sequence of k source blocks and we apply block by block our encoding function, and we get this resulting binary sequence. Okay? Now, each code word, f of x1, f of x2, etc., may be of variable length. So you cannot say a priori that, okay, then in order to read out and decode this sequence, I will take blocks of the binary sequence and decode each block, because I do not know, in general, what is the length. The length is a function of the input. So maybe this has length 3, maybe this is 0, 0, 1, and then this has a length 2, maybe it's just 1, 1, and then the next one is 4-bit, maybe it's 0, 1, 1, 0, and you copy like this. And now the question is, where do you put the commas, right? If we insert symbols like commas, so we parse the sequence, well, these symbols will cost bits. If you have to memorize, a sequence and you have to put a separator, the separator costs something, okay? So we don't want to do that. We want to simply have this binary sequence. And now imagine that the decoder will read this sequence from the beginning, and should be able to recognize that this is a code word, this is a code word, this is a code word. But how does it do it if those code words have a length that depends on the input, which is precisely what we want to recover, so we don't know it a priori. So we need a little bit of care. So these extension codes for variable length codes is not that simple. It's actually a relatively complicated problem that fortunately can be solved, and here is, well, we will see the solution in a moment. So we define a class of codes called uniquely decodable, okay? And we say that an NFG code is called uniquely decodable if its extension, as a star extension code, is one-to-one. One-to-one means that any output sequence of the extension corresponds to a unique input sequence of the K blocks. So in principle, what you can do, if we have a uniquely decodable code, independently of how many blocks we encode, so we do this concatenation, at the end, the encoder can take the whole big sequence and in some way find the corresponding unique source sequence that for which this corresponds. Okay. Now there is a apparently stronger condition that somehow directly implies unique decodability, which is called a prefix code. So we say that an NFG code is an instantaneous code or a prefix code if no code word is a prefix of another code word. For example, suppose that I have an alphabet with the 3 letters, 0, 1, 2, so this is X, and a code like this that maps 0 into the sequence 0, 1 into the sequence 0, 1, and 2 into the sequence 1, 1. Well, this is not a prefix code because 0 is contained as a prefix in the sequence 0, 1. So this means that if at some point, you have a sequence and a 0 appears, well, the decoder cannot make a decision here because it does not know what follows next, right? Next, it may follow, for example, a 1, and then the decoder may say, oh, but this is the code word 0, 1. Yes, but what about the next symbol is 1, 1? Then this could be 0, 1, 1, or, 0, 1, and then something else that we don't know. So basically, the decoder cannot just read out the sequence and as soon as it sees a code word, make a decision and find the corresponding output, say, source sequence for that code word. It has to look ahead until there is no more ambiguity, okay? And this may be, arbitrarily difficult. because you may have to wait forever until the end of the sequence, provided that the code is uniquely decodable. So instantaneous decodability means that as soon as you see a code word, bam, you can immediately make the decision. For example, another map of the alphabet 0, 1, 2 could be 0, 1, 0, and 1, 1. Okay? So now, no code word is a prefix of another code word. If I see a sequence, for example, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, well, the decoder immediately finds, sees a 0, is a code word? Yes, so that must be 0. Then sees a 1. 1 is a code word? No. Then 1, 0 is a code word, and therefore maps it into 1. Then sees a 1. Again, 1, 0 is a code word, make a decision. 1. 1, 1 is a code word, make a decision. 2. 0 is a code word, yes, 0. 0 is a code word, yes, 0. 1, 0 is a code word, yes, 1. So you see, the decoder can read out the sequence and immediately, as soon as it sees a code word, makes an instantaneous decision. Okay? So this condition, of the prefix condition, guarantees unique decodability, but does something more. It guarantees instantaneous decodability, which means you don't have to wait until the end or wait an arbitrarily large delay until you can make a non-ambiguous decision. As soon as the decoder sees a code word, it can make a decision. So this condition, of course, is very desirable. I mean, unique decodability is necessary. If the code is not uniquely decodable, then, of course, there will be, if we apply to a long sequence of blocks, eventually there will be 2 blocks that maps into the same sequence, and somehow, if the star extension code is not one-to-one, then we cannot guarantee the lossless condition. If the code is prefix, then, well, of course, unique decodability is guaranteed, but also there is one more property, which is the decoding is very easy. The decoding is instantaneous. You can make decision with minimal delay. As soon as you see a code word, you can make the decision. So now we look at a necessary condition that any prefix code must satisfy. And this is called the Kraft inequality, that turns out to be very useful in proving a sort of lower bound on the best possible rate of data compression. That's not the only way of proving these lower bounds. There are many proofs, many different styles of proofs. This is one of the most, say it's the simplest and the most classical. So this theorem, Kraft inequality, says the following: given the length function of a prefix code with block length n, this length function must satisfy this inequality. The sum of all possible source sequences of 2 to the minus their length is less or equal than 1. And also it says that conversely, given a set of integers satisfying this inequality, then we can construct a prefix code with code words of these lengths, which means it's not only a necessary condition, but it's also an existence condition. If you come up with a set of lengths that satisfy Kraft inequality, then there exists, you are guaranteed that there exists a prefix code with those lengths. Now, the proof is written here in a rather concise way, so I'm going to maybe add a few details. So basically the idea is to construct a binary tree of depth equal to the maximum length. So for a given code, there must be some L max, okay? Or vice versa, for a given set of integers, L1, L2, L cardinality of the alphabet to the end, there must be a maximum length. So we can construct this binary tree. Binary tree is a tree that contains a number of steps, and at every layer, at every node bifurcates. So at the end, and of course this is an exponential explosion, at the end, after L max layers, we end up with the leaves at this level, and those leaves are 2 to the L max. Okay, so those are all the leaves, the final nodes of this binary tree. Okay, now consider the following. Suppose that we have a prefix code. If we label this tree with 0, 1, 0, 1, 0, 1, so every time you go up is a 0, every time you go down is a 1, then, well, every final leaves here corresponds to a binary sequence of length L max, and they are all distinct, and in particular, it means that any code word corresponding to a sequence here ending at some point L, right? Well, this is a code word, so no other code word can be a prefix, so this code word cannot be prefix of no other code word, which means that all the sequences that originate from this node, right, are forbidden. There is no other code word that coincides with this blue code word up to here, and then it continues with a path here, because for this code word, it means that the blue code word terminating in here would be a prefix of that code word. So this is forbidden. So every code word identifies a subtree of forbidden sequences, which means that, you know, how many nodes we have in the, how many leaves we have in this subtree? Well, we have 2 to the depth, and the depth here is, well, the number of, let me write it this way, the number of leaves here in this subtree are 2 to the L max minus L, okay? And this has to happen for every code word, because we start with the assumption of having a prefix code. So it means that there must be another code word. Basically, all the code words of our code, there will be one at length L max, but every code word identifies a forbidden tree, a forbidden subtree like this, okay? And all these subtrees for every code word of length L, let's say LX, will contain a number of leaves of 2 to the L max minus LX, okay? So what it means? This means that if we sum the size of all the subtrees, there are all disjoint. There are no intersections of the leaves, because, of course, of the subtrees are disjoint. They are originated by different points in the tree. So if we sum the number of leaves of all these forbidden subtrees, well, these cannot be more than the total number of leaves. And so we have this inequality. The total number of leaves must be greater or equal than the sum over all the code words of the quantities 2 to the L max minus the length of the code word, which is the number of leaves in these forbidden subtrees. So now we can divide symbol term by term by 2 to the L max, and we get the inequality. Okay? So this proves that if we have a prefix code, then its length function must satisfy Kraft inequality. Vice versa, if I come up with a set of integers, L1, L2, that satisfy the Kraft inequality, well, then it means that I can find points, intermediate nodes in the subtree, such that those points have the property that they generated a subtree from each of these points are disjoint and and the size of the leaves sum up to less than the total size. So this means that I can actually construct a prefix code, because once I have these intermediate nodes, then the path going from the root to every intermediate node will be then the corresponding code word, and they have to satisfy the prefix code for the reason of before. No other code word can get, say, a certain path up to here and then continue from here to the corresponding to the end, or somewhere in between, because this will be contained in the forbidden subtree for that code word. Okay, good. So this is relatively easy to prove with this argument. There is an alternative proof that works also for countably infinite, say that when the set of length is countably infinite. Here we have assumed that the set of length is finite, and therefore there is an L max, and therefore we can construct the tree. But if suppose it may happen that we have countably infinite source alphabets, like for example, you remember that source that we computed the entropy of the geometric distribution. But the geometric distribution is has a well-defined entropy, but the number of symbols are all the integers, 1, 2, 3, 4, 5. So this is a countably infinite alphabet, and therefore, if we want to encode a source that is generated according to the geometric distribution, then we need basically a number of a countably infinite number of lengths. So that construction based on a certain tree of maximum length does not apply here. So there is another way of proving the Kraft inequality that works in this way. So given a binary sequence of length Li, right, I can associate this binary sequence to an interval in the interval 0, 1. So this interval is in general included in 0, 1. And this interval has as extremes the binary representation of the number 0 point B1, B2, B3, etc., BLI. So this is in binary. When you write in decimal, well, this will be simply every digit multiplies a negative power of 2 because those are to the right of the decimal point. So this decimal, this fractional number in binary corresponds to this number here in decimal. And if I add the last, add the size of the smallest last digit, basically I get the other extreme, because so basically, this interval is close to the left, open to the right. So every sequence identify a little interval, and the size of this interval, so the difference between these two numbers, is precisely 2 to the minus Li. Okay, so now it turns out that because of the prefix condition, these intervals are necessarily disjoint. So we have the interval 0, 1, and now every code word identifies a little interval of size 2 to the minus Li, and this interval is closed from the left, open to the right, and then there is another interval for another code word. This will be Lj, close to the left, open to the right, and another one, and another one. We can have all these countably infinite number of intervals, and those intervals are all disjoint. Well, it turns out that the total measure of these intervals is the sum of all their lengths, and since they are disjoint, this must be less or equal than 1, because the sum of, the measure of the interval 0, 1 is 1, and so we have that the sum over I, even if the sum is countably infinite of the length of those intervals, is less or equal than 1. Okay? Great. So, having Kraft inequality, we can prove in a very direct way the converse of data compression. What is a converse statement? In information theory, we look for fundamental limits. Fundamental limits means the best you can do to achieve a certain goal. For example, here we want to compress data and we want the smallest possible rate. And the converse statement means, well, whatever you do, no matter how clever you are, you cannot compress in a lossless way if your rate is less than some quantity. So this sort of universal lower bound. And then there will be achievability statement. Achievability statements are statements that prove the existence of schemes that achieve a certain rate. Of course, the best is when the achievability and the converse collapse, which means that yes, there is a fundamental limit and you can approach it as well as you want through some algorithms or some coding schemes that we can prove they exist. Then there is a third problem, which is code design, which is find those algorithms. And sometimes it's easy, sometimes, most of the time, it's very difficult to find explicit, computable algorithms that achieve as close as you want an information theoretic limit. Okay? So there are basically three components. One is the converse part, is what you cannot do. The achievability part is what you can do. Hopefully these two limits coincide. And then the third component is code design, which is data compression schemes, source coding, channel coding. So the algorithmic part. The algorithmic part is not really, we'll see many information theoretic results have a non-constructive flavor, because non-constructive means prove the existence of something without explicitly constructing it. Because the explicit construction is sometimes much more difficult than the proof of existence. So not always proving that something exists is that then immediately implies that it's easy to find computable algorithms that achieve what is promised by the theory. Okay? So at the moment, we start from here. I did this little introduction, so sort of overview, because I want to give you a little bit like the flavor of the general results that we will see in various, applied to various contexts in information theory. Now here we see the specific context of data compression. So the theorem, this theorem 7, says that the average normalized length of any NFG prefix code must satisfy this inequality. So in other words, the rate, the compression rate, is always greater or equal than the entropy of the source. And this result basically shows a fundamental operational meaning of entropy. Because at the moment, last week, I have defined the entropy as a strange quantity that may or may not make sense. Why the entropy is important? Well, it's important for this reason. It's important because the entropy is the fundamental data compression limit. It means that if you have a source that generates symbols and this source is compressible, I can find, well, we don't know yet, because this is the achievability part. But we know that there exists no scheme, no matter how clever, with a rate smaller than the entropy, and can still compress the source in a lossless way. It means that if you want to compress at a rate smaller than the entropy, you necessarily have to release the lossless condition, and you are going to introduce some form of distortion. But this will be something we will see later. Now, notice that at the moment the theorem is stated here for prefix codes. Okay? For prefix codes means you may say, well, okay, but what about if we get rid of the prefix code? Maybe there are uniquely decodable codes that do better than prefix code. So at the moment we are not sure that this entropy is the fundamental limit, is the fundamental lower bound, because we may consider a larger class of codes that are uniquely decodable but not prefix that would beat the entropy. We will see later that this is not possible. So this restriction to prefix codes in fact is not a restriction. Any code, any uniquely decodable code will satisfy the same limit. But at the moment we prove it for prefix code because we use Kraft inequality. So how the proof goes? Well, we consider the difference between the average length and n times the entropy. We use the definition of average length. We use the definition of entropy. This is minus the entropy. So notice that the source is memoryless. So n times the entropy is equal to the entropy of the vector source. Why is that? Well, because the source is memoryless, and we know that we can use the chain rule, right? We can write this in this form. But because of memoryless, the condition is ineffective because all the xi's are independent on all the others. So this is in fact the conditioning disappears because the source is memoryless. And then all these terms are the same because every xi has the same distribution px, so the entropy is the same. So this is just n times the common entropy h of x. Okay, so this is the writing for the minus the entropy of the vector source. You see that here we have the joint n-dimensional PMF appearing. Now what we can do is to basically write L as log of 2 to the minus L and put a minus in front. Of course, nothing changes, right? But now written in this way, we can basically collect these, we can introduce this term minus log of the sum of these 2 to the minus, and if we have a minus here, we need a plus there, so we introduce this denominator here. When you develop the logarithm, you see immediately these two terms cancel. So this is just an algebraic, sorry, algebraic manipulation. And at the end, what we find that the difference between this term and this term, if we define as a new probability distribution q sub xn given in this way, notice that these are probabilities because if I sum over all x's, well, I find 1, and those are all non-negative numbers. So this is a new distribution for over the alphabet xn. And if I consider the difference between this term and this term, well, this is nothing else than the divergence between pxn, which is the original distribution of the source, and this new distribution qxn given in this way. And then we have this last term here, okay? And now Kraft inequality says that this sum is less or equal than 1, which means that minus log of a number less or equal than 1 is positive. If we neglect this term, we get a lower bound. And finally, the divergence is positive, and therefore the whole thing is greater or equal than 0, which implies, of course, going back to the beginning, implies that Ln minus n times the entropy is greater or equal than 0, which is exactly the inequality we wanted to prove. Okay? So it turns out that with considerable more effort, you can see in the book of Cover and Thomas, for example, Kraft inequality holds also for uniquely decodable codes. So in other words, although we have proved Kraft inequality for prefix codes, because this tree argument or this binary expansion argument holds for prefix codes, it turns out that any uniquely decodable code also has to obey Kraft inequality. The proof is more difficult to do, and then I will skip it here. Okay? But what is the implication of this? The implication is that even if we relax the prefix requirement and we can expand in principle the class of codes to uniquely decodable codes, well, this theorem 7, still holds, because all what we have used in this theorem is that the lengths of the code, this L, satisfies Kraft inequality. Here, this is the point where we have assumed that Kraft inequality holds. So if Kraft inequality holds for any uniquely decodable code, it means that any uniquely decodable code also has to obey theorem 7, which means that this rate lower bound given by the entropy must be satisfied by any uniquely decodable codes, and therefore this provides a sort of a lower bound or converse statement for all possible uniquely decodable codes. Okay? So this tells also one thing, is that there is no point in trying to be more effective or more, let's say, efficient in terms of rate by considering non-prefix codes. Effectively, at least in this asymptotic regime of large blocks, we see that we can just restrict to prefix codes. There is really no big advantage, because any other uniquely decodable code which is not prefix would not give you a better rate, and of course the advantage of prefix codes is that they are instantaneous. So again, the big advantage is on the decoding side. The decoding is very easy, because the decoder can just read out the sequence, and as soon as it sees a code word, it can decode. Okay? So, what is this? Okay, so I guess we can stop here for the moment, because I don't want to make too long videos. If I make too long videos, then I cannot upload them, and the second half of this lecture will be in the next video.